MDM4U 8.2 properties of the normal distribution. So the normal distribution, many quantities are distributed symmetrically and unimodally about the mean in a bell-shaped curve. This distribution is known as the normal distribution. So regardless of the data set, you will have a mean. And the dispersion using standard deviations from the mean can describe how widespread that curve is. So it's symmetrical, left and right hand side are equal from the mean, and unimodal, there's only one peak. The population that follows a normal distribution can be described using two parameters, the mean and the standard deviation. Here you see standard deviations described using positive values on the right and negative values on the left. So, for any normal distribution, whether the data is closely tied around the mean, like you see on this right-hand side, very short distance between the mean and one standard deviation to the right, for example, or if it's a little bit more dispersed, if the standard deviation is larger, regardless, the area underneath the curve will be roughly or approximately the same. So the exact details don't matter. We won't need to memorize or use these numbers. But we're using the property that regardless of the shape or kurtosis of the curve, we're going to have that same relationship as far as our bell curve. The standard normal distribution. So the probability density function, which is actually the curve itself, if you were to plot that as a function, is given by this equation. And this allows you to graph the shape of the normal curve. However, integral calculus is needed to calculate the area underneath the curve to approximate probabilities. So, instead of needing to plot the normal curve of each and every single situation, one has been used as a standard with the calculations underneath the curve already calculated for you. So, the standard normal curve is normally distributed with mu set equal to 0 and the standard deviation set equal to 1. And this is our parent curve, the one that we will use to compare all different normally distributed functions. So normal probabilities can be approximated using a z-score. Let's look at this right here. We said that these in some ways are the same, even though their shape is not exactly the same, the kurtosis. So if you look at a point right here between the mean and the mean plus a standard deviation to the right, it would approximately have the same area underneath the curve to the left if we consider that the area underneath the curve is equal to 1 in each graph. So, that being said, a z-score is used to approximate based on how many standard deviations away from the mean a particular statistic is. So, a z-score table will be provided. It's used to approximate probability under the curve to the left of a particular z-value score. So, if we know the z-score value of a particular number, then we can use the following algorithm to find the area to the left of that point. So use the rows to find the z-score to the nearest tenth. And we're going to use this example of where we're finding the probability that the z-score is less than 1.12. So we're going to line up on the left column. We can get precision to the nearest tenth. That means 1 decimal place. We're trying to get this number, 1.12. So we can get as close to this with 1.1 to the nearest tenth. If we look at the columns, this adds precision to the nearest hundredth, or the second decimal place, tenths, hundredths. So to make 1.12, we 1.1 plus 0.02. And the intersection of these of the row and column will give you the area to the left of that point. Okay, so we can say that the probability of z being less than 1.12 is 0.8686. So the z-score representing the particular value in reference to its mean and how many standard deviations it is away. That's the z-score. This number represents the area underneath the curve to the left of that point. All right, we're going to describe three situations that you can have using z-scores. Predictions from a normal model. Less than. So if we are looking for an area that is less than a particular value. All that glitters, a sparkly cosmetic powder, is machine packaged in a process that puts approximately 50 grams of powder in each package. The actual masses have a normal distribution with mean 50.5 and standard deviation 0.6. The manufacturers want to ensure that each package contains at least 49.5 grams of powder. What percent of packages do not contain this much powder? So these word problems can be very lengthy, and the most important thing that we need to make sure of is that this distribution qualifies as a normal distribution. You'll just see in this question, the actual masses have a normal distribution, so that means that it is symmetrical, unimodal, and therefore we can use our standard normal curve to approximate areas underneath this curve. And let's take a look at how that's done. Mu for this case is 50.5, that's the average, and the standard deviation is 0.6 grams. So let's take a look at the particular statistic that we're looking at. We're saying what percent of the packages do not contain this much powder? We are referring to at least 49.5 grams. So 49.5 grams is on the left-hand side of the mean. So it's going to be a small probability. But what we need to do is look at how far away from the middle is this particular value. We can accomplish that using a z-score, and that's x, that's the particular value, minus the mean, mu, divided by the standard deviation. So we take a look at the deviation divided by the standard deviation, and we get negative 1.67. And we would have to use our z-score table. So this sheet will be provided. One moment. All right, so this page has areas to the left of the point for each of the different z-score values. So notice that there's two different pages. When we have negative z-score values, that would mean these values on the left-hand side. We'll use this page. When we get to our positive values, we'll use the second page. Notice that 0.00 would be equal to 0.5 because half of the area is on the left-hand side. So what we're going to do is look at our particular value. We have negative 1.67. So it's negative 1.6, and then 7, the intersection point is 0.0475. So we're saying that the probability that x is less than 49.5 for this particular situation is being approximated by, or is approximately, the probability that z is less than negative 1.67, and we determined that was equal to this value. Let's try another technique. Greater than. So we know that our z-score tables measure to the left-hand side. And if we want to be able to get the area to the right-hand side, what we could do is the following. We can calculate the area to the left-hand side. And if we know that the total area underneath the curve is equal to 1, then we can do 1 minus this area that we can calculate using the z-score table. So you'll see we do everything the same as the previous question as far as determining the z-score value of what is the probability that the first boy Giselle meets tomorrow will be taller than he is, and he is 168 centimeters tall. So this is described by this situation. We're going to do 1 minus the probability that it's less than. And if you do the z-score calculation, 168 minus 174 divided by 6, we get negative 1. And on our table, negative 1.00, negative 1.0, and the first column is 0, we get 0.1587. And we subtract that value that is known using the standard normal curve to get our area to the right-hand side. Last and final situation. If we are looking for the likelihood that a test statistic or a value is going to fall between an interval, so for example, A and B, what we can do is use this technique here. Subtract the probability that x is less than the larger value minus the probability that it's less than the smaller value. This will make sense visually using this graph. If you look at these 2 points, we could use the right endpoint and take the probability that the z value is less than that value, and then subtract the z-score of this value. And that difference between the two will give you the area in the middle for the interval. So in this case, we have our maximum value for the interval and our minimum value for the interval. And we'll do our max minus the min. We calculate the z-score for each of those results and subtract them. Good luck.